Yeah, actually, that day there was a bad, like heavy rainfall happening here, so there was a complete blackout after some time. So could not get back to you people. Anyway, today the weather is completely clear, so no chance of any such thing. Okay, so we were looking at combination of simple harmonic motions. Okay, so what we have seen so far is that if we have x1 or y1, whatever, they should be along the same axis. So the superposition of these two results in this calculation, for which we saw the derivation last time. If we expand it using that trigonometrical identities and all that, so we get that it ultimately becomes a net amplitude into sine omega t plus some net phase constant, where the net amplitude can be easily remembered by the Phasor diagram method. Like this, that if the phase difference between A1 and A2 is phi in radians, then the net amplitude becomes like the third side of a triangle, just like the vector addition triangle. This is called the Phasor diagram in this case, because ultimately we are not dealing with vectors. So we cannot call it a vector diagram, though it is identical to a vector diagram. And the net amplitude is given by square root of A1 square plus A2 square plus 2A1 A2 cos phi. And this angle, let's say epsilon, or you can give it any other name, alpha, beta, it doesn't matter. But the phase constant epsilon is tan inverse of A2 sine phi divided by A1 plus A2 cos phi. So this becomes a relation. Okay. So now moving forward, let's start with a simple example. So we have x1 equal to P naught sine omega t and x2 equal to find phi if the superposition of x1 and x2 results in a net amplitude of P naught, okay, or P naught root 3. So very easy type of question, but this type of thing is common at JEE mains level. Just quickly solve this using the above formula, then we'll continue ahead. Okay, so I think you should be able to work this out quite easily. Just send me the answers when you've done that. Started with the terms from SHM from HM. Okay, so let's look at the solution of this. It's pretty simple. You can see that in the A part, if you use the formula, so you can see that squaring both the sides, we'll get this. Okay, so this will tell us that cos phi should be half, rather minus half. Okay, so phi should be 2 pi by 3 or 120 degrees. And the corresponding phasor diagram will look like this. Your phasor triangle will become an equilateral triangle in this case. Okay, very simple. So similarly, just work out this next one also. Yes, very good, Tantrish. Answer is correct. For second part also. Okay, so it's just very similar process. Second part, you just substitute the net amplitude as this. So in the formula, you get this. So from this, you will get cos phi as half when you solve the whole thing. So phi will be pi by 3 or 60 degrees, and your phasor diagram correspondingly will be looking like this. So it's an isosceles triangle with the interior angle being 120, the exterior angle being 60. This angle will become 50 degrees equal to this angle. So here this will become the resultant of the superposition. So anyhow, I am sure this is pretty easy and clear for you. Okay, so next we'll move on to the last part, which is damped oscillations, before we can wind up simple harmonic motion. So damped harmonic motion. Now, before we get into this, just a point to keep in mind here, that this section is only for the JEE Mains syllabus. It is excluded from JEE Advanced. So damped oscillation occurs when a combination of a restorative force and a damping force. Okay. Example, viscosity or air drag, that type of force acts on a body where C is a constant and V is instantaneous velocity. Okay. So this is a 1D system along x-axis. Yes. Okay. So here what happens is, like, suppose we consider a body at some positive x coordinate like this and moving with a velocity like this, then there will be a drag or a damping force equal to CV in magnitude and opposite in direction. and there'll be a restorative force equal to kx acting like this. Okay, but the same thing if the body was at the same position, positive x, but it is right now coming back to the mean position, then the direction of the damping force will become opposite to the above diagram, because the damping force is opposite to the velocity. Okay, so this is a force proportionate to speed, okay, and opposite to velocity in direction. Whereas the restorative force is always opposite to displacement from mean position. So that acts towards the mean position. Okay. Likewise, if the particle is on the negative side of the mean position, that's a negative x, the restorative force will act like this, but the direction of the damping force will depend on the direction of velocity. It will be opposite. The velocity is like this, then the damping force will be like this. So when a combination of a restorative force and a damping force acts on a body in 1D motion along the x-axis, it results in damped harmonic oscillation. Not exactly related to friction, yes, because friction is independent of velocity. Na? Kinetic friction is mu n. So it is more related to viscous force, which you studied. If you remember Stokes' law, that we studied about viscous force or drag forces, which we had sometimes discussed about in kinematics, etc. That kind of thing. Okay, so now we can see that the dynamical equation for this.
Sir,
Yeah.
sir, I haven't copied it down
Okay.
completely.
Okay, finished?
1 second.
Yeah.
Done.
Okay. So now we see that the equation of motion for that becomes that the net force becomes the combination of restorative force and the damping force. So that should be equal to mass into acceleration, where acceleration is d2x by dt square. So we have the equation m d2x by dt square is equal to minus kx minus cv. And of course, v is itself dx by dt. So we can also write it as m d2x by dt square plus kx plus c into dx by dt is equal to 0 by bringing all the terms to one side. So this is the dynamical equation of a damped harmonic motion. Okay. So note in this, if you make c equal to 0, if the damping force becomes 0, then it is a regular SHM. There's no damping in that case. Okay. So now we define two technical terms for this. Okay. K by m is omega square. Okay. And we define something called damping coefficient gamma as c by 2m. Now this is something you'll have to memorize. Okay. There is no derivation for this at our level because the mathematics required for solving this kind of second degree differential equation goes beyond what our 10+2 syllabus allows. Okay. So you have to just over here memorize this term called the damping coefficient. Okay. And we will see the significance of the damping coefficient soon. You can see that this above equation, it corresponds to the free body diagram for either of the cases that we have discussed above. Now, solving the above dynamical equation for x as a function of time, we get three cases. Case one is called the underdamped case. So in the underdamped case, x is given by this kind of relation. So omega, this term, or rather omega 1, this term, is given by the relation So just note down up to here. I'll explain more about the underdamped condition. So here the condition for this underdamped case is that that then omega 1 becomes a real value. And the variation of x versus time becomes this sort of a graph. You can see that the equation that we got in this is like a diminishing amplitude. Okay. And this is a harmonic term. So it's got a diminishing or decaying kind of amplitude. So this is the underdamped case. So the underdamped case is a type of situation where initially the damping force is dominated over by the restorative force. Take this down, then we'll discuss the second case, which is called the critically damped case. And finally, the third case, which will be called the overdamped case. So these are the different types of situations in which damping plays a role in the damped harmonic motion. So it's not a perpetual oscillation. Eventually, you can see that the amplitude, even in the underdamped case, the amplitude eventually tends to zero. Because there's that exponential factor, e raised power minus gamma t. So eventually, it stops oscillating. And as time is progressing, it's oscillating, but with a diminishing or with a decreasing amplitude. Just a second, I'll verify that value. Yeah, that's correct. Just make a correction here, people. This should be K is greater than C by 4n. This will be the condition. Okay. Omega is greater than gamma. So C square by 4. This is the condition for the underdamped case. Now, K is equal to C square by 4m. Or omega is equal to gamma. This is the condition for critically damped case. And in critically damped case, what happens is that the x versus time graph, it doesn't look like an oscillation anymore. It looks like a all-out decay, straight decay kind of situation. Okay, and finally, the third case, which is actually very similar to the critically damped situation, is the one which is called the over damped condition. So in the over damped condition, basically K becomes less than C square by 4m, or omega becomes less than gamma. So the graph of this one also looks very similar to the critically damped case, but the difference is that this has sort of longer asymptotic kind of relation, whereas this dampens to 0 comparatively faster. So one of the reasons why this is probably not there in JEE Advanced is because the derivations of these are not part of our syllabus. So it just becomes a matter of memorizing the results. But yes, in JEE Mains, every alternate year or so, I have seen questions which are directly formula based on this. So you have to know this. Okay. You have to know that from a given equation, how you can calculate the damping factor, the critically damped condition, okay, the diminishing amplitude in the case of under damped case situation, etc. Okay, so with this, we complete SHM, and now we will move on to the next section of our physics syllabus, which will be wave mechanics.
Sir, can you please scroll it up just for a second?
Okay.
Sir, down. Yeah. Just one. Done.
So, yeah, so if any doubts and all are pending from module, etc., now you'll be having the physical doubt sessions week by week. So I would encourage you to come to the centers for physical doubt sessions and discuss them as much as possible. Because we have to move ahead in the syllabus also. We have spent a lot of time discussing doubts in SHM. Completed HC Verma almost problem by problem. So at this stage, that is more than enough if you complete HC Verma also. Okay, so first of all, we will understand what is a mechanical wave. It is a phenomenon such that a physical phenomenon, of course, such that energy propagates through a medium that is a material medium, like air or a string or the surface of a liquid solid, etc. So energy propagates through a medium through oscillations of medium particles. So any phenomena where this happens is categorized as a mechanical wave. And the most common examples of mechanical waves are ocean waves or ripples on a water surface, sound waves, through air or through any liquid or even through solids. Sound propagates through walls, etc., through rocks, walls, etc. Vibrations in a stretched
formulated
string or wire or anything like that. So these are all everyday examples of waves. Now, one more thing we should understand here is that light, X-rays, microwaves, cosmic waves, radio waves, etc. are examples of electromagnetic waves. These are not in the category of mechanical waves. So electromagnetic waves they involve electric and magnetic fields oscillating, not medium particles, not material particles. So hence they don't come in the category of mechanical waves. Okay, so now that we've understood the definition and seen some examples of mechanical waves, now we'll also see that on the basis of the nature of a mechanical
Sir,
wave.
1 minute.
Okay, we'll go back to that. Just give me a second. So mechanical waves are bifurcated into two categories, something that I'm sure all of you have seen before. Your understanding of waves from class 9th, 10th level. There is something, one category of waves is called the transverse mechanical waves, or here simply we'll call them transverse waves. So transverse waves are ones in which the medium particles oscillate along an axis which is perpendicular to the propagation of the wave. To the propagation of the wave. So most prominent examples of this is ocean waves, waves on the surface of ocean water, okay, then waves on a stretched string. So the medium particles oscillate perpendicular to the length of the string, whereas the energy of the wave propagates, or you can say the wave shape propagates along the length of the string. And the second category is, as I'm sure you're aware, longitudinal waves. And these are ones where the medium particles oscillate along an axis which is parallel to the propagation direction. We can, in brief, we can say that medium particles oscillate along an axis which is along the propagation direction. And a physical example of this is sound waves. So accordingly, we will now bifurcate this section into two individual chapters pertaining to each of these. Longitudinal waves and transverse waves. We will start our study of wave mechanics with the study of transverse mechanical waves. And for that, the physical example of transverse mechanical waves we consider is waves that propagate through a stretched string.
सर एक सेकंड और ऊपर करो.
Right. Okay, done with this, beta. Okay, so let's start with the first section of mechanical waves over here, which is the chapter of transverse mechanical waves. The physical model of this that we will study is waves on a stretched string. Okay. So the idea is that if we, for example, have a long string which is rigidly attached at both the ends, so one end is very far away, so it's extending to infinity, and this end is x equal to 0. So this is a string which has a tension of T in newtons and a linear mass density or a mass per unit length of mu in kilograms per meter. Now, if we create any sort of a disturbance in the string, like we create a pulse like this by plucking one end of the string, what we observe is that this pulse travels along the string at a constant speed. A simple experimental observation. So now if we create a series of pulses by making the end O oscillate up and down, then what we'll see is that a series of pulses with peaks alternating like this on the positive and negative side of the mean position. This kind of a shape travels along the string. So after some time, we'll see the shape of the string has become like this. Then further after some time, we'll see that the shape of the string has become like this. This whole shape is traveling like this. Whereas here, what we'll see is after some time, this pulse is reached here. Then after some time, the pulse has reached here. This pulse is traveling like this. So now this kind of phenomena has to be represented by a general equation. So that is what we look at next. So just make a note of this. This is a one-dimensional medium for propagation of transverse waves. That is a stretched. So this is a single pulse. And now this is a periodic wave propagates due to oscillations at the end x equal to 0 along the y-axis. So this wave propagates along the x-axis. This is our x-axis. This is our y-axis. Whereas medium particles oscillate along the y-axis. This is an example of a transverse wave phenomena because the wave is propagating along the x-axis, whereas the medium particles are oscillating up and down along the y-axis. These are two different kind of situations in which there is a transverse wave phenomena that is happening along a one-dimensional medium. In one case, a single pulse traveling along that medium. In another case, a periodic wave that is propagating continuously along that medium. But that periodic wave is causing the medium particles to oscillate in the transverse direction or along the y-axis here, which is perpendicular to the axis of propagation, which is the x-axis. Okay, so now next thing what we will see is how to write a general equation to represent the above phenomena, which is basically a one-dimensional transverse mechanical wave. Okay, this is 1D, stands for one-dimensional. That means it's propagating along a one-dimensional axis. That is, so we will develop this idea next. The general equation of a one-dimensional transverse mechanical wave. Now, in order to develop this idea, we have to do some background work. So first of all, we have to understand transformation of graphs from graph theory in maths. So the transformation, so there are many different types of transformations of graphs in maths that you would have seen. But here the transformation we will understand is simply that if the graph of a function y is equal to fx, suppose it looks like this, but we want to transform it such that the shape remains the same, but it shifts, okay, along the x-axis by a distance d. Then we have to replace x with x minus d. Simple example of this is that we, for example, have a parabolic graph like this. Y is equal to, let's say, 4 minus x square. And we want to transform it like this. Such that the whole graph is shifted by 3 units. So you can see this will become y is equal to 4 minus x minus 3 whole square. We have a graph, let's say, like this. Y is equal to 1 by x. Now we want to shift this graph so that this point is 1 comma 0 now. So this you can do by just replacing x with x minus 1. So the whole graph shifts by 1 unit like this. So this is just transformation of graphs along the x-axis. Simple concept that we are first reviewing from maths. Similarly, for example, if we have shift a graph along the negative x-axis. So let's say we are looking at the graph of y is equal to x square. And we want to shift the whole graph. Let's say 2 units like this, then we have to replace x with x plus 2 whole square. So to shift a graph in this direction now, I want to shift it by distance d like this, then I should just replace x in the formula with x plus p. Whereas to shift it along the positive x direction, I have to replace x with x minus p. So this is a simple concept of transformation along the x-axis. So within transformation of graph theory, we'll require only one type of concept, which is this one over here, for our purpose for wave mechanics sake today. Okay, now The only slight difference is that when we write a maths function, for a function in maths, y is equal to fx. X and y are both real numbers. Okay, they are dimensionless. Okay, they are unitless. Okay, so, for example, we write the function y is equal to sin x. Here, x is a number, does not have any unit. Okay, and y is a number between -1 and 1, but it's a real number. It is unitless. But in a physics equation, x and y are typically physical quantities. So they have dimension and unit. So, for example, if x is a length or distance in meters, and y is also a length or distance in meters, then the equation y is equal to sin x is incorrect. It is dimensionally invalid. We have to represent it by, it has to be modified to something like this, where a and k are constants such that they have dimension of length and dimension of length inverse respectively. Okay. Because in the equation y is equal to a sin kx, you can see that dimension of y is equal to L. Dimension of kx should be dimensionless because it should be, kx should be an angle. Okay. And dimension of sin kx is also unity. Therefore, dimension of y should be equal to dimension of capital A on the other side, which should be length. So, in general, if y and x are of dimension length, then the function has to be of this type, where k is a constant such that kx is dimensionless, or k has dimension of length inverse. Okay. And a simple example of this function is this one. I'll just minimize this part a little bit. It's more about understanding. You did not write down the whole thing in detail.
Excuse me, sir.
Sir, can you go a little bit?
Yes, I'll scroll up a bit also, but as I said, like this, Achal, you want to understand this transformation of graphs part first, no? Okay, so just go through this, then we'll discuss the part about the dimensionality also. Okay, so now keeping this in mind, when we are looking at,
Sorry, sir, 1 minute.
okay, yeah, people done with this now? Okay. So just the last thing here. So if we have an equation of this type, which represents a function in which x is a length dimension. So it is in meters or centimeters or whatever. Okay. Then the function will have to be represented like this. Okay. And then if we want to transform it such that it's transformed by a distance d, or let's say if we transform it by a distance which is specifically delta x. Okay. So we want the whole wave shape to shift by a distance delta x. X has to be replaced with x minus delta x. So this is to shift along the positive x-axis by delta x. Okay. Now suppose this shape is traveling at a constant speed v. So for a graph traveling along the positive x-axis at uniform speed v, then its shift becomes vt in time t. So the equation of that shifting graph, it becomes f of k into x minus vt, or we can write it as y is equal to f of kx minus omega t, where omega is a constant. So here k was a constant which had dimension of length inverse. So here omega is equal to k into v. So omega is a constant which has dimension of time inverse, because v is of course having dimension of velocity. So k into v will have dimension of time inverse. So this now represents a traveling shape. And is traveling along the x-axis at a uniform speed of omega by k. So we will see that we use equations of this form. Okay, equations of this form where y is a function of x and t such that it is a function whose argument is of the type kx minus omega t. When it represents this, it represents a traveling shape along the x-axis, traveling at a uniform speed of omega by k. Okay, so we'll conclude today's session here, and next time we'll pick up the basics of one-dimensional traveling waves, equations, etc. from here onwards. So just taking a conceptual understanding and introduction into this section of physics. So that's it for today's session, people. Wish you all the best. Have a nice day and a nice weekend.
Bye, sir. Thank you, sir.